So the next type of decay will be gamma decay. So this is going to be gamma decay. Now you have to understand this particular process, which is very important. Gamma decay is different from alpha and beta because here in gamma decay there are no release of any protons, neutrons or electrons. So in gamma decay there is no release of any protons, neutrons or electrons. But what happens in gamma decay? Gamma decay, as a result of gamma decay, it produces electromagnetic radiation. It produces electromagnetic radiation, which we call it as the gamma rays. Which we call it as the gamma rays. Now, you have to understand the very basic of gamma decay. So, like alpha and beta, we don't have any release of any protons, neutrons or electrons from the nucleus of an element. But what happens is, gamma decay is a kind of electromagnetic radiation that releases gamma rays. Now, I hope you might have learned about the electromagnetic radiation in your lower classes. These electromagnetic radiations travel in the form of wavelength. I hope you know. This is your wavelength, wherein we have wavelength which is represented by the symbol lambda, wherein you have crest and trough like this, and gamma rays have very high frequency and it is of a very short range wavelength. Okay, so you have to understand this. So gamma decay is a kind of electromagnetic radiation that releases gamma rays. Okay, and this gamma rays is actually, as we all know, it is an electromagnetic radiation which occurs in the form of wavelength with a very high frequency and a very short range of wavelength. Now, what do you mean by this high frequency and a short wavelength? We have to understand that. Now, if you speak about the basics of this, I am saying, for example, we actually get light from sun. That is a very common thing which everybody knows. Sunlight is the ultimate source of energy for the entire earth, for all the living organisms present. Now, you have to think about a very important concept here. Why does the sunlight is actually having different types of electromagnetic radiation? Sunlight is the one source which actually has the different forms of electromagnetic radiation, including gamma rays. It also has the visible range. It also has ultraviolet rays. It also has X-rays. It also has infrared rays, okay, something like this, okay, and your gamma rays comes here, okay, your gamma rays comes here. So these are the different examples of electromagnetic radiation, okay. So from sunlight, we actually get this particular range, which is called as the visible range. Now this visible range ranges from 400 to 700 nanometer. So the visible range is from 400 to 700 nanometer. Less than 400 to 700, less than 400 is going to be UV. Okay, it is going to be UV, that is 200 to 400 nanometer. Okay, and when you take 10 nanometer, it is X-rays, and when you take less than 10 nanometer, when you have less than 10 nanometer, we have the gamma rays. We have the gamma rays. 1 minute. Okay. So this is the basic idea of gamma rays. And another important point which you have to understand is, in gamma rays, there is no transmutation. There is no transmutation. Why? Because if there is no release of protons, electrons or neutrons, an element will not change. So there is no transmutation. Simply an element will release gamma rays. Say for example, the elements present in the sun, they are able to release a particular component called as solar flares. If you take sun as an example, from the sun, as I told you, we have the ultimate source of energy. There are some elements in the sun which are able to produce solar flares. What do you mean by solar flares? We have to understand. It is very simple. Solar flares are actually happening because of the release of gamma radiation. Okay, solar flares are released from is a process which actually involves the release of gamma radiation. Okay, and what happens during the formation of solar flares? The brightness or the intensity of the sunlight is going to increase like anything, and because of that, the temperature on the earth is also going to increase like anything. And this actually happens for a few seconds to minute. That is called as solar flares. Please understand. The brightness of the sun is going to increase suddenly for a few seconds to minute, and after that it's again going to decrease. So during the increase in the brightness of the sun, it actually releases the gamma radiation. It is going to release the gamma radiation. It is preferred that, it is mentioned that we are not supposed to see the sun directly when it is going to release this solar flares. That is going to cause problems with the nerves of your eyes. Okay, so we are not supposed to see the solar flares wherein it is going to release the gamma rays directly. So and most importantly, this solar flares is very commonly seen in places where the temperature is extremely high, not in places like Bangalore or any other places wherein we always have a very long winter season. Okay, it is actually noted in places where you have a very long summer, and you could see the temperature of those places extremely high. So that is called as solar flares. So this solar flares is actually a process of release of gamma radiation from the sun. Okay, from the sun for a few seconds to minute. Okay, so that is going to be solar flares. So this electromagnetic radiation, that is gamma ray, has a very high frequency and it has a very short wavelength. Now the point is, you have to understand, uh, you know, say for example, this is one particular wavelength that I tell you. This is another kind of wavelength. This is another kind of wavelength. Okay? We actually term this can be taken as a short wavelength, this is a medium wavelength, and this is a long wavelength. Now you have to understand that based on this difference, we have different electromagnetic radiation. Based on the differences in the wavelength, okay, we have different electromagnetic radiation. Okay, so this is actually more of electromagnetic radiation. It is not important, but then please understand, gamma decay is actually different from alpha and beta decay, wherein there is no release of electrons, protons, and neutrons. There is no transmutation. It simply consists of electromagnetic radiation that releases gamma radiation, and this gamma radiation ranges less than 10 nanometer, and it is actually very near to X-rays, and it has a high frequency and a short range wavelength. Okay, it is a high frequency and a short range wavelength, and it is actually seen in sun with a process called the solar flares that actually releases the gamma radiation. And finally, I want to conclude that this gamma radiation has more and more penetration power when compared to alpha and beta particles. So with this we are coming to the end of this gamma decay as well. Okay. Now, moving on. So we will just finish out this decay. 1 minute, some background noise is coming. Okay, now listen. We will conclude this process of decay by adding a note on its penetration power. So I told you that gamma decay has, gamma radiation has more penetration power when compared to alpha and beta. So we will just discuss how. So speaking about penetration power, we will take an example. We will take paper. We will take aluminum, and we will take lead. So this is going to be paper. This is going to be aluminum. And this is going to be lead. Now, if you could see this in this simple diagram, when we place a paper, aluminum and lead, simultaneously, when we allow alpha particle to pass through, alpha particle cannot even penetrate through paper. Okay? And when you place beta particle can penetrate through paper, but it cannot penetrate through aluminum. And if you take gamma particle, sorry, we should not mention it as particle, it is gamma radiation. So this gamma particle, it can penetrate through paper, it can penetrate through aluminum, but it cannot penetrate through lead. So this is the penetrating capacity of alpha, beta and gamma. As I told you, beta radiation has much more penetration power when compared to beta. Beta particle has much more penetration power when compared to alpha. So this is the penetration power of alpha, beta and gamma radiation. Okay, so with this we are coming to the end of this radioactive decay process. Now, moving on, we will go with the uh, measurement of radioactivity. Measurement of radioactivity. Now, speaking about the measurement of radioactivity, 1 minute. Yes. Now, this is another important topic which we are going to discuss. Um, the radioactivity of an element is measured in the terms of dps. It is measured in the terms of dps. Now, what is the expansion of dps? It is expanded as disintegration. It is expanded as disintegration per second. It is expanded as disintegration per second. That is the rate at which the radioactive nuclei means singular, radioactive nuclei disintegrates. So the radioactive activity of an element is measured in terms of dps. dps is expanded as disintegration per second. That is the rate at which the radioactive nuclei disintegrates. Okay. Now we actually represent this mathematically as AC is equal equal to dN divided by dt. dN divided by dt. Now, AC is the radioactivity and dt is the nuclei, sorry, dN is the nuclear disintegration. Nuclear disintegration. dt is the time duration of the nuclear disintegration. Okay, so AC is the radioactivity, dN, as I told you here itself we are explaining it, it actually implies the nucleus. So the nuclear disintegration, dt is the time duration of the nuclear disintegration, okay, which is a mathematical representation of the measurement of radioactivity. Speaking about the units used for the measurement, units used for the measurement of radioactivity, we actually use becquerel. We use becquerel, which is BQ, and 1 BQ is equal to 1 dps. Here 1 BQ is equal to dps is nothing but disintegration per second. Okay, dps is disintegration per second. 1 BQ is equal to 1 dps. So this is the predominant use of the unit, that is becquerel. Other units of radioactivity includes Curie and Rutherford. Curie and Rutherford. Okay, so those are the other units of the radioactivity, but the most commonly used one is becquerel. Okay, so with this we are coming to the end of the measurements and units of radioactivity. Now we will discuss about the Jyotis in the admin waiting room. Okay, Jyoti left. Okay. Now moving on, we will move to the next topic, which will be the applications of radioisotopes. Actually, I should start Geiger-Müller counter today as a continuation of measurement of radioactivity. But if I start Geiger-Müller counter, I cannot, end up without completing. Wherein you will also find it difficult to understand in this class. So you will take a complete class on Geiger-Müller counter. So now we will go with the applications of radioisotopes. Very simple and easy. Applications of radioisotopes. Now, The applications of radioisotopes is actually classified into three major categories, or we take it as four major categories. One is the field of medicine, next one is the field of agriculture, and then in the field of industry, and finally we will also speak something about the role of radioisotopes in the field of molecular biology. So since we are the life sciences, I have just added with this particular area. This actually comes along with the medicine, but then I have added separately. Okay, now speaking about the applications of radioisotopes in the field of medicine, uh, we will just quickly have some examples, very simplified examples I'll tell you. The radioactive sodium with mass number of 24 and atomic number of 11 is used to detect the clots in the human body. So the radioactive sodium is the one which is used to detect the clots in the human body. We also have cobalt with a mass number of 60 and atomic number of 27 is able to produce gamma radiation that is used to kill cancer cells. We will also have one more example, that is iodine with a mass number of 131 and atomic number of 53 is used to analyze the functions of thyroid gland. Is used to analyze the functions of thyroid gland. Now these are the predominant simplified examples of applications of radioisotopes in the field of medicine. Now basically when we use these radioisotopes in our body, we also have side effects. Now if you take cobalt, which actually produces gamma radiation, that is able to kill the cancerous cell absolutely fine, but it is also going to kill the normal non-cancerous cells. Okay? It is also able to kill the non-cancerous cells without necrosis or any problem. So that cells are also killed with this particular kind of isotope, radioisotope. And even radioactive sodium is able to detect the clots in the human body, but then it actually sometimes mixes with the blood components like WBC, and it actually causes a risk of blood cancer even. Okay, so we have the advantage. At the same time, there is always a risk of the use of these radioisotopes everywhere. Even when we are going to discuss about agricultural applications, there are many side effects. Okay, we actually have many advantages in the field of agriculture. We're producing disease-resistant plant, yield of the plant is increased, this and that we used to say. But then the effect of radioisotopes will always be there, and it is also going to cause an effect on our human body. So natural is always a natural, and whenever you use chemicals or the chemical elements like radioisotopes, it is going to cause hazardous effects in our body. Same as the case in industry, maybe it cannot have some advantages. It has less advantages in the field of industry. And in the same time of molecular biology also it has advantages when compared to disadvantage. But then the handling of the radioisotopes is very tough. Okay, so these many disadvantages also we have, but then since we are discussing about the applications of radioisotopes, we should not think about that. These are the applications of radioisotopes in the field of medicine. Now, we will discuss about the application of the radioisotopes in the field of agriculture in the next class. Now, the session is open for discussion. If students have any clarifications, you are welcome to clarify your doubts. All right, if there are no doubts, we will end the class, but then please, once again, I'm telling you, try to understand the concept, don't by heart or mug it up blindly. That is not going to help you in the case of learning and understanding. So please try to understand the concept, read more books so that you will get a better understanding about the recent trends of radioisotopes. So thank you so much. We'll see you in this class.
Thank you, sir.
Thank you, sir.